So, number 36 out of the packet. We're dealing with a Morris taper. Now, I mentioned the other day in class that there are standard tapers out there. The Morris tapers are one of those sets of standard tapers. A number 4 Morris taper is defined to be 0.62326 inches of taper per foot. So what that means is this inside surface here, it's a circular surface. Every foot of length, the diameter would change by 0.62326 inches. So it's a very, very subtle taper. This, by the way, is actually a problem that was put out by the GM Corporation for industrial training about 14 or 15 years ago for training I helped out with for them. So anyway.
Excuse me, is the taper then
the taper is, yeah, this hole here is the diameter of that hole per foot of length. So the top of this hole is 1.231 inches. The ball itself has a diameter of 1.2 inches. So the ball is a little bit smaller than the top of the hole, so it's going to sit down into the hole. What we basically need to find here is how far does this ball then stick up out of the surface of this material. Well, this is not a simple problem. I'm going to magnify the ball and its contact with the surfaces a little bit. I'm going to exaggerate the angles. One of the things that we learned from our geometry from last semester is if you have a circle, a line that is tangent to the circle intersects the radius at a right angle. So if I draw a radius from the center of the circle out to where that line touches it, that's perpendicular. That's a right angle. We know that there's a slope here on this surface. To figure out what that slope is, we have to convert this taper into a slope. That taper is saying that the diameter changes by 0.62326 inches per foot. So we need to convert that diameter into a radius so that we can get what the slope factor is here. Well, a radius is just half of the diameter. So half of 0.62326 would be 0.31. What is that? 163. Does that look right? There we go. That is inches per foot. So that's inches per 12 inches is what that slope is on one side. Actually, I got those backwards. This should be down here and the 12 over there. So 0.31163 to 12 is that slope factor. What that means is since this is perpendicular, we talked a little bit about perpendicular lines last semester having the opposite reciprocal of the slope. So all that means is the rise and the run interchange. So at the slope factor here, the 0.31163 would be here compared to 12. We know the length of this is the radius of the circle, or half of the diameter. The diameter is 1.2, so this is 0.6 inches. So now we can use that information to find this dimension and this dimension. How are we going to do that? Well, I'm going to take this slope factor here, the slope ratio, and I'm going to use it to create a right triangle that's going to be similar to this right triangle. This right triangle has dimensions, as we said, 0.31163 to 12. I can find the hypotenuse by doing what? Pythagorean theorem. So 0.31163 squared plus 12 squared equals, I'll call that x. No, I don't want to call that x. X is what I'm looking for here. And we'll call that y squared. So the square root of 0.31163 squared plus 12 squared. Now, realistically, this is not going to be much different than 12 because that's really small. The 0.3 is really small. So there it is, 12.004 is what we're ending up with there for that dimension. That triangle there, as we said, is similar to this one. So now I can find this dimension right here and this dimension right here. We'll call this A and B. How do I find dimension A? I have the 0.6 goes to 12.004 as A goes to 12. So you can see A is probably going to be just a little bit less than 0.6. 0.6 times 12 divided by 12.004. 0.5, well, it ends up being 0.6 if we round it off to the nearest thousand, because that rounds up. So we're going to call that still 0.6. B, same proportion. 0.6 goes to 12.004 as B goes to 0.31163. You know what, let's do this. I'm going to make that 0.5998 just to, we're going to go an extra decimal point. Just to preserve a little bit of a difference there. So down here, 0.6 times 0.31163 divided by 12.004. 0.0156 we're going to go with. So what that is giving us is the distance from the center of that ball to where it intersects the side. We know now that the diameter here where this ball intersects the sides of this hole is going to be twice this. So let's double that, 0.5998 times 2 gives us 1.1996. So that's the diameter of the hole now where the ball makes contact with it. Now the hole started out with a diameter of 1.231. And the taper has to take it down to 1.1996. So we're going to subtract there. So that's 0.0314 inches that that taper has shrunk the hole. So we need to figure out how deep you have to go into that hole now to get down to move that much. Well, this goes 0.62326 inches per 12 inches. How far do we have to go 0.0314 inches? You'll now cross, multiply, and divide. Does that make sense how I set that up? The standard Morse taper is saying the diameter change is 0.62326 inches for every 12. We want to know how far do you have to go to make the diameter change that 31.4 thousandths. So 0.0314 times 12 divided by 0.62326. So 0.6046 inches is how deep that has gone in. So now it's time to analyze all that we have here. Pretend that picture is legible. So from the center of the ball down to where it contacts the hole, it is the 0.6046 inches. No, wait, I'm sorry. That's not it. From the top of the hole to where the ball contacts the hole. So from the top of the surface to where the ball contacts the hole is the 0.6046 inches. From the center of the ball to where it contacts the hole was 0.0156 inches. And then, of course, from here up is 0.6. Where did 0.6 come from? From the center up is just a radius of the ball. So we're going to add together these two dimensions here, 0.6156 inches. We're going to subtract the 0.6046 inches. To get 0.011 inches, or 11 thousandths of an inch, which means that ball, in reality, is just barely sticking up over the top of the hole. Now, in this diagram, is that what they were asking for? Sort of. What they really are asking for is, yeah, this is 4 1/8 inches here. How far is it from the bottom up to this top of the ball? So we have to take 4 1/8 plus 11 thousandths. How do we do that? Convert. Convert what? Perfect. Good job, Jared. 4 1/8 inches is 4.125 inches. Plus 11 thousandths is 4.136 inches. Doesn't that one look like a lot of fun? That one may or may not appear on a quiz again someday, like tomorrow.
Now, how do they use this in actual practice, this concept here?
Well,
Putting
the Chrysler Corporation, they used as a depth gauge. They would have a standard taper and they would use a diameter ball. They would actually drop that ball in there to create very precise.
okay, so they actually would measure this
Yes,
final measurement.
Yep.
Putting
And-
the ball into that taper.
yes. And it was, for them, it was, for designing like ball joints and stuff like that in cars. For these guys, it's actually probably a step above what they're ever going to use. But if you were to, what's that? Okay. Okay. Where do you work at? Okay. So you guys actually do it. Right? For the most part, as a CNC operator, this would be a step above what you would really need.
So you do have a chart that we
Well, the engineers figured our measurements out, but for doing our fault, that's the actually do that, but somebody else figures out all the measurements.
Yeah, it's just like,
Go by that.
like an inspection will provide a no road go.
Yeah.
You're like,
You're going to drop it in and figure out if it's
Yeah, so
above
yeah.
height. Yeah.
the engineers are gonna.
Yeah. But this is one of the best ways if you're producing ball bearings or something that has to be precisely round and precise to a precise diameter. This is one of the simplest ways to test is you drop it in and see if it sticks up and rotate it. I mean, you can test more than one surface at once. So let's look at some of the other problems in this packet. For example, after yesterday, you guys should have been able to do number 40 now, a pulley system. I'm going to draw it just a little bit more simplistic than what it is on the paper, just for the sake of time here. So we start off, we have a 4-inch pulley running at 1800 RPM, which is turning a 6-inch pulley, which is attached on a shaft to a 3-inch pulley, which is turning a pulley of unknown size, which is at 1300 RPM. And we want to know the size of that final pulley. So we want to know the size of this pulley right here. How do we start this problem? So we're going to go from the 4-inch pulley to the 6-inch pulley, and mathematically, how do we do that? Careful, this is an inverse proportion, remember? So it's a constant product, not a constant ratio. So it's going to be size times speed. So 4 times 1800 is going to equal 6 times whatever the speed of the 6-inch pulley is. So it's not cross multiply and divide anymore, it's just multiply and divide. It'll be 4 times 1800 and then divided by 6, which should give us 1200. So the 6-inch pulley is at 1200 RPM. The 3-inch pulley is also at 1200 RPM. Why don't we have to use a formula? They're on the same shaft. They have to turn the same RPM if they're on the same shaft. It's the transition through the belt that causes the change in RPM. Now what? So 3 times 1200 is for the 3-inch pulley, goes to, what's it?
1300.
So yeah, we have an unknown diameter times 1300. We have the known RPM. So again, it will be a multiply and divide, only this time it will be 3 times 1200 is 3600, divided by the 1300 RPM. So 36 divided by 13 gives us 2.77 inches. So there's a diameter of 2.77 inches. How many of you got that one right? How many of you had that one done? If you wanted to do it as a ratio, you could. If you were doing this as a ratio, of course, it's 4 to 6 is the size of the pulleys. The 1800 goes with the 4, but since we know this is an inverse proportion, we put it on bottom instead of on top, and then it's multiply and divide again. Just to me, these ratios, these proportions don't make much sense because the 4 and the 18 go together. Why aren't they together? To me, a ratio is a proportion is supposed to have relationships in both directions, and when it's an inverse relationship, there is no relationship horizontally. It's a flipped relationship. It's always been confusing to me. But if it works for you, go with it.
Did that just come out of your mouth?
What's that? It's always been confusing.
Something mathematical was confusing.
Well, I mean, I always it's always been confusing to me how to teach to someone else how to remember that. I've always remembered it, but explaining to someone else that, okay, because it's an inverse relationship, you got to flip it. It's easy to say it, but it's difficult to make someone really understand it. So that's why I've never used proportions for an inverse relationship. I always like to use a constant product. They have to, the distance traveled by a point on this pulley has to equal a distance traveled by a point on this pulley because that belt is moving the same distance on each. So the distance is the size of the pulley times the number of turns it makes in a minute. That's how far that point goes in a minute. So that to me that makes sense because there's two things that have to be constant. Okay, how many of you had number 41 done? You did? What'd you get? Perfect. 840 RPM for number 41. Number 42. This is actually a relatively simple slope problem. Pretend my drawing here isn't horrible.
You know that you're artistically challenged. You're mathematically gifted.
Definitely artistically challenged. Yeah.
Can't be both.
I don't know. Da Vinci was a great
I was
mathematician.
just thinking the same exact thing, man.
You don't know. No.
So on this one, we can find this distance right here. How? So 3 to 1 slope. Where's the 3 1/4 go? On top. Good. And it will be cross multiply and divide. 1 times 3 1/4 divided by 3 will be 1 1/12. Anybody want me to work through that calculation, see where that came from? You guys okay with your fractions? 1 1/12? 1.0833. Okay. So now, that is 1 1/12 off of each side, or 2 1/6 total from 5 to get x. So 5 is 2 5/6, or x is 2 5/6 inches. What do you think? Not too terrible? Bless you. Now, number 4, anybody have number 42 right? There you go. You guys are depressing me. Nobody's raising their hand on these.
I raised my hand.
Did you? You had that one right?
Oh, I know one.
Number 41.
I had to raise my hand once per class.
Just to make sure the deodorant's working for the morning.
We're good.
43. Anybody have an answer for number 43 that they want to venture? See if they did it okay?
I found Y for 50 thousandths.
Okay. Did you find X?
No, because
Okay.
tapered thing.
That's similar to this first one.
Yep. See if I can draw a picture that's somewhat reasonable here. Pretend that looks round.
I like your A.
Yeah. Pretend it looks round. It's the projector distortion is the problem. It actually looks round on my screen. We're going to go with that story. So again, the key is that the radius of that circle has to make a right angle with that tangent surface that it sits on there. And we are given that that is a 1-to-1 slope here. The diameter is 0.15, so this is 0.075 inches. We know that since this is 2 inches high here, or 0.2, sorry, thank you. What's a factor of 10 among friends? So that means if it's 1-to-1, that has to be 0.2 inches from here to there as well. And since, of course, it is given as 0.25 across there, this has to be 50 thousandths. So that gives us Y. Now to the challenging part. Like before, we got to break down the horizontal and vertical here. I'll call this A and B. To do that, I'm going to use my 1-to-1 slope. I'm going to create a right triangle out of that 1-to-1 slope. Guess what we're going to do here? A squared plus B squared equals C squared. 1 squared plus 1 squared equals that dimension squared. It comes out to be 1.414. Now that we know that, we can find A and B here because 1.414 goes to 0.075 as 1 goes to A. So it's 0.075 divided by 1.414. Giving us 0.053. And since that's 1-to-1, this is going to be 0.053 over here as well. What good does that do us? Well, it tells us that from here to here, we have a total distance of 0.075 plus 0.053, which is 0.128 inches. Which means from here to there, we're going to subtract the 0.05, which gives us 0.078 inches. It's 0.078 from here to here. Guess how far it is from here to here? It's 1-to-1, so 0.078. So now what we have, we got 0.078 here. We've got 0.053 there, and we have 0.075 here, just the radius of the ball. So our total height is found by adding those up. Which is going to give us 0.206, correct? So if that's 0.206, that means that sticks up above here. If we subtract the 2 tenths here, 0.006 inches above the top. What do you guys think? You're being awful quiet today. Does that mean you're tired or you just don't get it?
I don't get it.
You don't get it?
I'm not having a hard time understanding where these numbers are coming
I'm gonna go and watch on YouTube about 4 times.
Okay.
Especially when you're setting up those proportions like 1-4-1.
The big trick when you're dealing with a lot of these, the trick is you take that slope triangle. This is a 1-to-1 slope. Oops, 1-to-1. You take that slope triangle or slope factor or whatever, aspect ratio, and you turn it into that right triangle. And once it's a right triangle, now you can find this imaginary hypotenuse here by doing, if I call that m or whatever, 1 squared plus 1 squared equals m squared, and you can solve for m. And that's how we got that 1.414, was we solved that. Once you have this complete right triangle, now I can use that to compare to anything else that has that same slope. Since this is perpendicular, it forms a right angle there, I know that that has to have the same, well, actually the opposite reciprocal slope, right? But this is 1 to 1, so this is 1 to 1. If, let's say it came like this, let's say that this was a 2 to 1 slope, well, this is going to be a 1 to 2 slope. It just changes the vertical and horizontal change. They switch spots when you have a perpendicular. Does that make sense? If this one rises 2 for every run of 1, this one's going to rise 1 for every run of 2 because they're perpendicular.
So our slope triangle that we made, we're comparing that to that triangle inside the circle that we.
Yeah.
That's not really.
And technically what we really want was the slope of this line in the circle. In this case, both of them were 1 to 1, so it didn't matter. This triangle describes both this surface and the radius of the circle. If it wasn't a 1 to 1 slope, if this was a 2 to 1 slope like this, what we would have used is this one, a 1 to 2, because that describes this line. Technically, it would have been a 1 to 2 like this. Does that make sense? So that's the triangle then we would have used to describe that line. So then it would have been 1 squared plus 2 squared that we would have used.
So then when we have, how do we set the proportion correctly?
So once we have this, we look at that radius. Now that we know that the radius of this goes at those ratios, we know that the radius is 0.075. Well, we need to find the rise and the run from the center of the ball to that point of tangency. So we just label them, like I just called them A and B. And we know the two sides that correspond here are the hypotenuse of this slope triangle and the radius of the ball, because those are the angled surfaces. So it doesn't matter which order. I can either go 1.414 to 0.75, or I can go 0.075 to 1.414, either way. It's just these two sides are linked together, so I'm going to put them in a proportion. So now the rest of that proportion, the other ratio of that proportion, is going to be whichever side I'm looking for. Let's say I want to find side A. Side A goes with the 0.075, so it has to go on bottom because they're from the same triangle. These are the real dimensions, and the top numbers are the slope triangle dimensions. So on top, A is horizontal, so the horizontal dimension here is just 1. So you cross multiply and divide, that gave you A.
Basically all the steps, side steps we're doing.
Yep.
Everything we've done in like last week. Right.
Yep, and a little bit of last semester. Yeah. That's why I'm doing these examples, because it does bring in a lot of review from last semester. And it shows you, I mean, in a couple weeks we're going to start doing trig, and trig could break these problems down. But I like doing these examples because it shows you that even without the trig, you can solve some very complex problems just by using similar triangles. All the trigonometry is taking a certain set of known right triangles and known ratios of the sides. All it is similar triangles. It's just we know that if a right triangle has a certain angle, well, the ratio of the sides is a certain ratio. And that's all trigonometry is. So this is basically, we're doing trigonometry without defining sine, cosine, and tangent. We're just taking known right triangles and comparing to them.
Okay. We're doing it the right way. Now we use one at a time.
Yeah.
Thanks, Tom.
You bet. Okay, well with that, did anybody take a stab at number 45 yet? You tried?
That would be a couple things.
Oh, and that involves some of this again.
Yes. 45 involves all of this, plus you're going to have to do a system of equations. Anybody who can get me the correct answer to number 45, it is a 20-point bonus question.
I found two variables.
So just so you know, Dave, if they ask you about that one, hands up.
I can do half.
Make checks payable to the David Hildebrandt Retirement Fund.
That bid off that 1,000 points.
Okay, so moving on then. On to the 46 through 53. How many of you have those done?
You had a packet yesterday.
Nope, this is the same packet. This is the one that looks like this. This is from, the front page looks like this. Okay, so if you guys haven't completed those, I am going to pick some problems that I'm going to go over. I'm going to do number 59. Number 59 is saying an actual length of an object is 4 foot 2 inches. The length on the drawing is 1 1/12 inches. What is the scale of the drawing? So is it a 1/64th, a 1/32nd? What is that scale? So the scale is always the drawn length to the actual length. So we have 1 1/12 over 4 foot 2. However, when we have a ratio must be two things that are the same units. A scale factor is a ratio. There are no units on a scale factor. It's 1 to 32 or whatever. It's not 1 inch to 1 foot or anything like that. Like for architectural, it is a rate, not a ratio. But for mechanical, it's always a ratio. So this 4 foot 2 down here has to be converted into inches. Well, 4 feet is how many inches? 48. 4 times 12 is 48. Plus 2 would be 50. But we still have to do some conversions. 1 1/12 to 50 is not a proper scale factor. It's a 1 to something is what we want. So how do we make this 1 to something? Well, we're used to making a denominator 1. If we wanted the denominator to be 1, we just divide by whatever the denominator is, right? We want the numerator to be 1, we just divide by whatever the numerator is. 1 1/12 divided by 1 1/12 is 1. So now we have to divide 50 by 1 1/12. So make that 50 over 1 divided by the 1 1/12 has to become an improper fraction. So 1 times 12 is 12 plus 1 is 13/12. Then what? Take the reciprocal and multiply. Good. The 50 over 1 doesn't change. 13 over 12 becomes 12 over 13. We can't cross cancel anything. So 50 times 12 is 600 over 13. So we're going to convert that back into a mixed number. 13 goes into 60 how many times? 4. 4 times 13 is 52, which is 8. Bring down the 0. 13 into 80. 6 would be 78. There's 2 left over. So that is a 1 to 46 and 2/13 scale factor. I know that's not terribly realistic, but that's what it comes out to be. Number 64 is one I want to look at. Actually, I want to look at 63 and 64. Just because these two point out some very subtle differences. Number 63, we have a gear with 91 teeth running at 240 RPM. It is being driven by a gear that is turning at 840 RPM. And I want to know how many teeth it has. How do I set this up? Is this a direct relationship?
Yeah.
If the number of teeth goes up, does the speed go up or down? Speed goes down. So this is an inverse relationship. So this is not going to be a ratio. It's not going to be a proportion. It's going to be a constant product. So it's set up as size times speed. 91 times 240 equals, over here I don't know the size, so I'm going to call the number of teeth x times 840. So this is going to be 91 times 240 divided by 840. And you're correct, 26 teeth. Number 64, the reason I'm doing the two of these together is because it'd be really easy to treat these two problems the same, but they are quite different. Number 64, two gears have a gear ratio of 2.8 to 1. If the larger gear has 84 teeth, how many teeth does the smaller gear have? Is this going to be a direct or an inverse? It's direct. I am given the gear ratio and I'm given the number of teeth on one of the gears. So it's a 2.8 to 1 gear ratio. The 84 is supposed to be with the larger gear, so it'll go on top. So now it'll be 1 times 84 divided by 2.8. We get 30 teeth. So the smaller gear has 30 teeth. So what if I have just an example of, let's say I have a 5-to-2 gear ratio, and the larger gear is turning at 680 RPM. And I want to find the speed of the smaller gear. Is this going to be direct or inverse? This is direct. No, this is not direct. Up here I had a gear ratio and I was relating it to the number of teeth. That's going to be direct. Down here, however, I have a gear ratio and I'm relating it to the speed, the RPM, which is going to be inverse. Whenever relating the number of teeth and the RPM, it's going to be inverse. Or the size of a pulley to RPM, it's going to be inverse. Does the 680 go with the 5 or the 2 tooth in the ratio? Larger gear, so it goes with the 5. It doesn't matter whether we know how many teeth are in the gear. We know that the ratio of teeth is 5-to-2, so we can use the 5 and the 2 to do our calculation. It's 5 times 680 equals 2 times whatever that speed of the smaller gear is. Will it be going slower or faster than 680? Better be going faster. So 5 times 680 divided by 2 is, what was it? 1700 RPM. Good. Do you see the subtle difference between those last three? Very confusing because they look like very nearly identical problems, but each of them gets handled differently. You got to remember, when you have gear ratios, if you're trying to find out the number of teeth and all you have is the gear ratio and the number of teeth, well, it's a direct relationship. You're setting up a proportion, cross, multiply, and divide. But if you have gear ratios and you have the number of teeth and RPMs being mixed together, then it's going to be an inverse. Anytime you bring in the speed or the RPMs, it's an inverse relationship now. I think we shall call it a day at that. For tomorrow, I want you to come in and I want you to be complete up through, you should be good up through number 85. Tomorrow in class, we'll discuss the temperature stuff a little bit, and then we're going to take a quiz.